Hello everyone. Today I'm going to talk about discrete Fourier transform and its properties associated with it. So let me share my slide first and then we can discuss about um, discrete Fourier transform and its properties as I said before. Okay. Okay. So discrete Fourier transform. So it is very similar to discrete time Fourier transform, but at the same time, there are some differences involved as well. So discrete time Fourier transform, DTFT, as we know, is defined by capital X of e to the power of j omega is equal to summation of n goes from minus infinity to infinity x of n e to the power of minus j omega n. Okay. In the case of discrete Fourier transform, because the signal is finite duration, so the analysis equation is given by x capital X of k. So in this case, it is capital in DFT, it is capital X of e to the power of j omega. Here it is capital X of k. Summation of n goes from 0 to capital N minus 1 because the signal length is n, x of n e to the power of minus j 2 pi k by capital N times little n. We call this as n-point discrete Fourier transform. K goes from 0 to n minus 1 inclusive. Okay? And if you recall the DTFT, so how I remember this formula is instead of capital X of e to the power of j omega, I put capital X of k. Summation is there, but instead of n going from minus infinity to infinity, since it's a finite length, I put n is equal to 0 to capital N minus 1. X of n is obviously same in both. In DTFT, it is e to the power of minus j omega n. Here, you replace omega by 2 pi k by capital N. Okay, so if you do that, then you get this endpoint discrete Fourier transform. Now, all the time writing e to the power of minus j 2 pi k by n times little n might be a little tedious. So that's why there is a twiddle factor which is called as a W of n. The properties associated with W of n, we will explain to you in later, is given by e to the power of minus j 2 pi k by capital N. Now the entire expression over here can be simplified by this. So the entire over till this point is the same. Now, instead of e to the power of minus j 2 pi k by capital N, we put Wn, and then this k times little n is k times little n. Again, k goes from 0 to n minus 1 inclusive. Okay. So this we call this as an analysis equation. So the synthesis equation is given by x of n is equal to 1 over n summation of. So here, what you do here is you have 1 over n summation of k. Now, because x of k is given, x of k, because you have DFT coefficients, k goes from 0 to capital N minus 1. Now, e to the power of plus j 2 pi k by capital N times little n. Again, n goes from 0 to capital N minus 1 inclusive. So we call this as an n point in inverse discrete Fourier transform. Again, I don't want to write e to the power of j 2 pi k, e to the power of j 2 pi by n all the time. So I can replace by saying this as w minus k n subscript of capital N. Again, n goes from 0 to n minus 1 inclusive. Okay. So, in other words, we have a n point DFT pair, which is x of n. If I take an n point DFT, then I get x of k. With x of k, if I take n point inverse discrete Fourier transform, I get x of n. Clearly, because of the basis function, DFT in general will be a complex number. So capital X of k is equal to capital X of r of k plus j times capital Xi of k. So this is a real part and the imaginary part. So if I want to take a magnitude, as you know, is the square root of the real part, square of the real part plus the square of the imaginary part. So if I want to take an angle, it is nothing but tan inverse of imaginary divided by the real part. So if I want to write the magnitude and the angle together, then this is going to be capital X of k is going to be the magnitude, x of k magnitude, e to the power of j, angle of capital X of k. So the angle is computed like this and the magnitude is computed through the above formula. Now, what I'm going to do is, I'm going to do a very basic thing. So I'm going to compute a 4-point discrete Fourier transform of x of n. X of n is given by this expression, this sequence, which is 0, 1, 2, 3. So upward arrow indicates that n is equal to 0 term. So I want to compute a 4-point DFT, which is nothing but capital X of k. So what is the length? Length is going to be 4 because this is 1, 2, 3, 4. Okay. So my k will go from 0 to n minus 1. So 0 to 3. So I go back and put it in the analysis equation, which is given by capital X of k is equal to summation of n goes from 0 to 3, x of n e to the power of minus j 2 pi k by capital N. Capital N is 4 times little n. Now I expand the summation. So n is equal to 0. Obviously, I'm going to get this term has 1, but x of 0, the value is 0, so I don't include that term. K n is equal to 1, so this term is going to be 1 here, this one, and then the value is 1, so you have e to the power of minus j 2 pi k by 4. Then n is equal to 2, so x of 2 is 2, then e to the power of minus j 2 pi k by 4 times 2 plus n is equal to 3, x of 3 is 3, then e to the power of minus j 2 pi k by 4 times 3. Now, what you do is that you substitute the value of k. K is equal to 0 in this expression. You are going to get capital X of 0 is 6. K is equal to 1 in this expression. So you are going to get minus 2 plus 2j. Then k is equal to 2. You are going to get minus 2 in this expression. And then finally, k is equal to 3. X of 3 is going to be minus 2 minus 2j. Okay. So overall, final answer would be capital X of k is 6 minus 2 plus 2j minus 2 minus 2 minus 2j, and upward arrow indicating k is equal to 0. This is a 4-point discrete Fourier transform for a sequence given above. Now, given a discrete Fourier transform, which is x of k as 1, 0, 1, 0, I want to compute x of n, right? So that means that I need to compute a 4-point inverse discrete Fourier transform. So again, little n would go from 0 to n minus 1 inclusive. So n goes from 0 to 3. So again, what you do is that you go back to the synthesis equation. X of n is equal to 1 over n. Summation of k goes from 0 to n minus 1. Capital X of k e to the power of j 2 pi by capital N times k times little n. So 1 by 4, this is a 4, the length is 4, 1 by 4. Summation of k is equal to 0 to 3, x of k e to the power of j 2 pi by 4 times kn. Again, is the same logic. What you do, you expand the summation of with respect to k. So the value here is 1 and 0. So 1, 0, 1, 0. So that means that k is equal to 0 and k is equal to 2 term will be there, right? K is equal to 0 term would be there here. So this is going to be 1. K is equal to 0 is, this is always obviously is going to be 1. K is equal to one term is 0, so this is going to be 0. K is equal to 2 term is 1, so e to the power of j 2 pi by 4 times 2n plus 0. Okay, so this term is going to be 1, and this is e to the power of j pi n. E to the power of j pi n, as you know, e to the power of j pi is minus 1, to the power of n would be minus 1 to the power of n. So finally you get 1/4 within bracket 1 plus minus half to the power of n. Okay, so now you substitute the values of n. N goes from little n goes from 0 to 3. So little n goes from 0 to 3. So when n is equal to 0, n is equal to 0, what happens to this term? This is going to be 1 plus 1, so this is 2 by 4, half. Then for odd value of n, the value is going to be 0. So that means that 1 and 3, the value is going to be 0. For even value of n, it's going to be half. Okay, I hope this is clear so far. Now, so given the sequence was given, we were able to compute either discrete Fourier transform or inverse discrete Fourier transform endpoint. Okay, now I'm going to give you a few more examples. In this case, x of n is given as delta of n minus n naught. In this scenario, what we do here is we go back to our regular expression to compute the endpoint discrete Fourier transform. So n point meaning that n can be any value. In this case, it cannot be 4, unlike in the previous example. So capital X of k is equal to summation of n goes from 0 to capital N minus 1, x of n, wkn, subscript of capital N, k goes from 0 to n minus 1 inclusive. X of n is given by this expression. We know that x of n minus n naught is going to be 1 for n is equal to n naught, and n not equal to n naught, the value is going to be 0. So the entire summation goes up. What you left it with is wk n naught n. What is this? Is e to the power of minus j 2 pi by capital N. That's how it is defined. And then k n naught, which is put up here. So the point here is delta of n minus n naught. Its DFT is w k n naught capital N. If I want to put it in an exponential term, it is e to the power of minus j 2 pi by capital N k times n naught. Okay. Now I'm going to take another sequence. Again, it's x of n is a to the power of n. N goes from 0 to n minus 1 inclusive and 0 otherwise. We want to compute an n point discrete Fourier transform. Again, go back to the regular formula. This is the formula. Okay. Now instead of x of n, I'm going to put a of n. Okay. E to the power of minus j 2 pi by capital N k n. Now you have to apply a geometric series sum with a finite sum. Okay, all right. And so this is going to be simplified as 1 minus a to the power of capital N e to the power of minus j 2 pi k by capital N. This small n, little n, would be replaced by capital N. So you end up with e to the power of minus j 2 pi k divided by 1 minus a e to the power of minus j 2 pi by capital N times little k. Simply applying the geometric sum for the finite expression. Okay. Now I'm going to make the signal a little shorter, meaning that uh, x of n is given. If the value is 1, n goes from 0 to n2 minus 1 inclusive, and 0 from n greater than or equal to n2 minus n2 by 2 till n1 minus 1. So that means that till n0 to n2, n by 2 minus 1, the value is 1. The rest, the value is going to be 0 for an n point DFT of x of n. Again, it's the same thing. You put in the expression for n point discrete Fourier transform, which is capital X of k summation of n goes from 0 to capital N minus 1 x of n wkn capital N, k goes from 0 to n minus 1. Now because from n by 2 to n minus 1 the value is 0. This summation can be replaced by n is equal to 0 to n by 2 minus 1 e to the power of minus j 2 pi by capital N times kn. When k is equal to 0, this is going to be 1. So if this is 1, summation of n goes from 0 to n2 minus n by 2 minus 1 of 1. That expression is going to be n by 2. And for k equal to 1, equal greater than or equal to 1 to k less than or equal to n minus 1, again you will apply a geometric sum expression. So in this case, this is little n is going to be n by 2. So this is 1 minus e to the power of minus j 2 pi by capital N k. This is going to be n by 2. So n by 2, 2 by n by 2 get cancels out. You have e to the power of minus j pi k divided by 1 minus e to the power of minus j 2 pi by capital N times k. Okay. So this is the few ways of, these are the basic signals where you can compute the discrete Fourier transform. Okay. All right. Now, this is a very important conceptual idea which I am going to present. Before that, as by definition, we know that x of k is equal to summation of n goes from 0 to n minus 1 x of n wkn times capital N. It's an endpoint DFT. So discrete Fourier transform. Whenever the term Fourier comes, we always think about frequency response, because we know that the Fourier transform gives you the frequency response of the signal. So how is this k related to frequency? Okay. So before I go into that, this expression is exactly the same thing. Instead of w capital N, we write e to the power of minus j 2 pi by capital N. In some of the books you might see this, some of the books you might see this, or in other books you might see the combination of the two. Okay. So the question is, how is k index related to the frequency omega? So omega is given by 2 pi k by capital N, where k, as we know, is an endpoint. K goes from 0 to n minus 1. So now, so that means that, so omega will, so how many values of omega you will get? How many values, different values of omega? So omega would be n different values of omega will be getting. So what is the range of omega? It can be 0 to 2 pi or minus pi 2 pi. So around the unit circle, you are going to get n different values of omega. Now, is there a way I can increase the number of omegas so that I can get a better frequency resolution? So meaning that I can get more number of omegas, and thereby I can get a better representation of my frequency representation of the input signal. Answer is yes, through a process of zero padding. What we do here is, given x of n, where n goes from 0 to n minus 1, it should be inclusive. Okay, make sure that you do that. Zero padding refers to the operation of extending a signal of length n to a length m, where m is greater than n. So in other words, I'm going to define a variable x, z meaning that zero padded of n is nothing but x of n, where n goes from 0 to n minus 1, and then it takes the value 0 when n is greater than or equal to n and less than or equal to m minus 1. So it means that, so this is my signal, okay, but I'm going to take m point DFT. So by doing that, in the denominator, I will have omega is equal to 2 pi k by m now. In that, because the denominator is getting larger. Okay. So if the denominator is getting larger, so that means that I will get more dense point of omega around the unit circle. So This is what I'm explaining here. So remember, we are doing an m point DFT. X of k is equal to summation of n goes from 0 to n minus 1, because afterwards the values are 0. X of n w k n m. This is nothing but summation of n goes from 0 to n minus 1, x of n e to the power of minus j 2 pi by capital N times kn. K goes from 0 to m minus 1, both inclusive. Now the omega here is 2 pi k by m. So more frequency points will be computed around the unit circle. So we will get a better frequency resolution. So the concept of zero padding is very important in terms of the fact that, so the issue with practical signals would be, we don't know what frequency component exists in the signal. Okay, so say for example, if suppose someone is drilling, or some fan noise, okay, or a train noise which is coming, if I want to study the frequency component of that particular signal, so we really don't know what kind of frequency component do exist in the signal. So in that case, it's always better to have a higher frequency resolution. Thereby what we can do here is that we can apply zero padding. Thereby we, by with better frequency resolution, we may come closer to the true representation of the frequency that exists in the signal. We may come closer, we may not hit the actual value. Okay, that we need to understand. Now again, x of k, as I mentioned before, it has a magnitude as well as the phase response. The x-axis here is the k index. Now if you want to put it in the frequency response, so you can put it in the frequency with the transformation of 2 pi k by n. 2 pi k by n. Now, as an exercise, what I want you to do is, I want you to compute an 8-point DFT of the sequence. X of n is 1 1 1 1, 4 ones, and this is at n is equal to 0. It's an 8-point. If you see that, since it's an 8-point, but there are 4 values, so that means that clearly you append 4 zeros at the end. So 1 1 1 1, 4 zeros. Okay, so then you can compute x of k, you can compute your magnitude, and you can compute the angle. These are the answers which are given. Okay, so take this as an exercise and try to solve it, so that you can have a idea about how to actually use the analysis and synthesis equation. Now, all the time putting the expression, expanding either n or k, and then substitute either k and n to get these values, which we have done it in the examples which I have discussed before as a sequence. Is there a way I can put it in a matrix format so that I can compute it lot faster? So the answer is yes. There is a concept called as a discrete Fourier transform as a linear transformation. So it's a linear operator, so we can apply a linear transformation. So n point DFT is given by this expression. Now assume that n is equal to 4. So I want to have a 4-point DFT. So this is x of k is equal to summation of n goes from 0 to 3, x of n w k n 4. Now you expand the k value as well as the summation of with respect to n. K is equal to 0, so this is going to be always be 1. So this is x of 0 plus x of 1, x of 2, and x of 3. If k is equal to 1, this expression is k's value is 1. So x of 0, then x of 1 is x of 1, this is w14, plus x of 2 w24, plus x of 3 w34. Similarly, x of 2, x of 0, x of 1, w2, 4, and 6, x of 3, this is 3, 6, and 9. Okay, so if you want to put it in a matrix format, so capital X of 0, 1, 2, and 3, little x of 0, 1, 2, and 3. The first row and the first column is always 1. Then you start off with, this is because it's a 4-point, so subscript will always be 4. So you start off with 1, 2, and 3. So in other words, you're starting with 1, 2, so on to n minus 1. So in this case, it's 3. Then you multiply by 2. So this is becomes 2, 4, 6. Then in order to get the fourth row, you multiply by 3. So this becomes 3, 6, 9. If there is a fourth one, if it's a if there is a fifth one, if it's a fifth 5-point DFT, then you multiply by 4. 4, okay, 8, 12, like that. Okay, so this is a 4-point. So this is capital X in a matrix format is nothing but W4 of little x. So in other words, capital X, which is the DFT value, which is a 4-point DFT coefficient, is nothing but W4 times X, which is your input sequence. So in general, capital X is equal to WNX. Wn is called as a n-point DFT coefficient. So capital X will go from x of 0, x of 1, so on to x of n minus 1. Little x will go from x of 0, x of 1, so on to x of n minus 1, because it's an n-point DFT. So how is W n defined? W subscript n. As I said before, the first row is going to be 1 and the first column is going to be 1. Okay. Then n will always be there at the bottom. So W1 to n minus 1. Then this is you multiply by 2. So 2, 4, 2 times n minus 1. Last one you multiply by n minus 1. So this becomes n minus 1. This is 2 times n minus 1. This term will become n minus 1 times n minus 1. So this is an n by n matrix. So capital X is equal to WNX. So if I want to compute the inverse discrete Fourier transform, then what I need to do is little x is nothing but Wn. You take the inverse of that and multiply by capital X. So what is Wn inverse is nothing but 1 over n. This 1 over n you have to put it in such a, because of the fact that in the synthesis equation you have 1 over n term is there. And then how do you take the inverse of this? This is nothing but you have Wn is there. Wherever you see a W term here, you multiply minus 1 here. This is minus 1 within bracket minus n minus 1. So which is what I'm doing here. Okay. Wherever you have a W term. Okay. So Wn inverse is nothing but 1 over n Wn conjugate, because of the minus here, because you know that it is e to the power of j term. So because of the minus, so you are bringing in the conjugate term. Okay. Okay. Now comes the twiddle factor. Okay. Twiddle factor, which we call it as Wn and its properties, because this is very important for us to understand the properties associated with it. Wn, which is nothing but e to the power of minus j 2 pi by capital N, is nothing but cos of 2 pi by capital N minus j sine of 2 pi by capital N. So we know that the magnitude response is going to be 1 and the angle is going to be minus 2 pi by capital N. Now here I am going to substitute some values and try to see some properties associated with the twiddle factor. Wn n by 4 is nothing but e to the power of minus j 2 pi by n, which is nothing but the twiddle factor for Wn multiplied by n by 4. So n gets cancels out, so you end up with e to the power of minus j pi by 2, which is nothing but minus j. Then Wn n by 2 is nothing but e to the power of minus j 2 pi by n by 2. So this is going to be minus 1. Similarly, W3n by 4 n is nothing but j. Wnn is going to be 1. This is a very important property. Wk plus n is that can be broken down into Wkn multiplied by Wnn, which is nothing but Wkn. Okay. Then the sixth one is Wk plus n by 2n can be again be broken down into Wkn, Wn by 2n. Wn by 2 n is minus 1. So that's why you have minus of wkn. Okay. W2kn is nothing but e to the power of minus j 2 pi by n within bracket 2k. Now I'm going to do a very smart thing. What is this about is this can be put up as e to the power of minus j 2 pi n by 2k, because if I put n by 2, so this is nothing but 2k. So what is this all about? This is nothing but wkn by 2. So it means that an n point DFT, you are breaking down into n by 2 point DFT. This is a hallmark for the fast Fourier transform algorithm. Based on this, we do a decimation in time and decimation in frequency concept. Okay. And then the conjugate, as I have discussed before, is nothing but W minus 1. Okay. Now, if I go back to the 4-point DFT, 4-point DFT, this is the expression. Now, every time I cannot solve all these expression because I had to put in the calculator, get the values. But can I simplify this? Answer is yes, because it's a 4-point. We know that WK plus N is nothing but WKN. So what this is saying is WK plus 4 is nothing but WK. So if k is equal to 0, then W0, W4, W8 are same. K is equal to 1, W1, W5, W9 is the same. I'm not talking about the 4 because 4 is the same. So because we are doing an endpoint here. So what this, and when k is equal to 2, then 2 plus 4 is 6, plus 4, 10, because it's a 4-point. Now 3, k is equal to 3, W3 plus 4, 7, plus 4, 11 will be the same. Now, this is the expression for W4. I want to simplify this. The first row is 1, the first column is 1. Now, 1, 2, and 3 I cannot simplify. 2 I cannot simplify. 4 is minus 4 if I do, then it becomes 0. 6 is there. It goes beyond 0 to 3. Then I can subtract by minus 4. Okay, so this is minus 4, this becomes 2. I cannot do this. This becomes minus 4, which is 2. And then this is minus 4, this is 5. Again minus 4, you do, this becomes 1. Okay, so that means that I only need to compute 1, 2, and 3 values. 1, 2, and 3 values. I don't need to compute 9, 6, 4, okay, other values. So I can make sure that I can use this formula, which is WK plus capital N is equal to WKN. So finally, I'm going to just substitute. I'm going to get this expression. All ones, the first row, first column, all ones, and then these are the values. Now, if I have to compute a 4-point DFT, x of n cos of pi n is equal to minus 1 to the power of n. N goes from 0 to 3 inclusive, which we already know. So if I substitute the value, I'm going to get this. Now I have capital X is equal to W4 matrix, which is W4 matrix here. And then this is my sequence. This is simple matrix multiplication. I get 0, 0, 4, 0, which is going to be this. Okay. Now, I hope you have understood the analysis and synthesis equations for endpoint discrete Fourier transform. What is the concept of zero padding? Why do we require zero padding in practical sense? The third and the most important thing is that how a discrete Fourier transform can be used for in linear transformation. Now, today what I'm going to do here is I'm going to talk about discrete Fourier transform properties, and there are some very important properties attached to this specific transform. So as you might have seen in signal systems, there are so many properties for continuous time Fourier series, continuous time Fourier transform, discrete time Fourier series, discrete time Fourier transform. So those properties are there. Also, you might have done Laplace and Z transform as well. Now, looking into this properties, in general, why these properties are required? These properties actually helps you to solve the problem a lot faster. Number one. The second one is that from a student perspective, they might think that, oh my God, there are so many properties are there. But if you look at a little closer, there are a lot of similarities between the two, between any of these properties. Like if you talk about discrete time Fourier transform and discrete Fourier transform, but at the same time, there are some dissimilarities also. And from a student's perspective, you need to know what are the similarities and dissimilarities associated with it. Okay, the first property is periodicity. So if x of n and x of k are n point DFT pair, then capital X of k plus n is equal to capital X of k for all values of k. Another one is similarly little x of n plus capital N is equal to x of n for all values of little n. So means that x of k would be the same if you repeat after n, capital N. X of n would be same if you repeat after capital N. Okay. So it's periodicity because of the periodicity term attached to it. The second one is the linearity. So as you have seen it in the other properties as well, the same thing applies, but in a discrete Fourier transform. X1 of n, its n point DFT is capital X1 of k. X2 of n, its n point DFT is capital X2 of k. So it's a times x1 of n plus b times x2 of n. Its n point DFT would be a times capital X1 of k plus b times capital X2 of k. That's a pretty straightforward principle. The third one is called as a circular time shifting. This is a little tricky because the circular time shifting comes because of the periodicity, because it's periodic with a period of n. Okay, so x of n is n goes from 0 to capital N minus 1 inclusive. You might have heard time shifting property, but now there is a circular time shifting because it is with respect to the periodicity information, which is a modulo n we talk about. So xc of n is given by x of n minus n. This is the expression modulo n. So we call it a circular shift with respect to modulo n. So if you have been given an example, as an example, x of n, 1, 2, 3, 4, 5. So in this case, the capital N is 5. You make a circle here, x of n. So index is x of 0, 1, 2, 3, and 4. So the index does not change, but the values would alter, meaning that x of 0 is 1 in this case, 2, 3, 4, and 5. This is x of n. So x of n minus 2 modulo 5 in this case would be, what you are doing is that as if you have a knob here, index value would be remain the same. You take the knob anti-clockwise two times, 1 and 2. If you move it, 1 and 2, if you move it, then what happens is x of 3 value will come at n is equal to 0. Okay, and then x of 4 will come at n is equal to 1, x of 0 will come at n is equal to 2, x of 1 will come at n is equal to 3, and x of 2 will come at n is equal to 4. So in other words, you are going anti-clockwise direction, you take a knob 2 times, okay, anti-clockwise. So value would be 4, 5, 1, 2, and 3. So in other words, what we say is that since it's 2 here, minus 2, so you take the last 2 samples and put it at the front. So meaning that 4, 5, 1, 2, 3. So this is the answer which you are going to get, 4, 5, 1, 2, 3. Mathematically also you can do it. How do we do mathematically is xc of n. Mathematically is xc of n is equal to x of n minus 2 modulo 5. Okay. So now you substitute the value, n is equal to 0. xc of n is nothing but x of minus 2 modulo 5. So this is nothing but 5 minus 2, which is x of 3. So what is your x of 3? This is 0, 1, 2, 3. X of 3 is going to be 4. Okay, value 4. So x, so now n is equal to 1, so x of 5 minus 1, so x of 4. Then n is equal to 2, so x of 0 modulo 5, which is going to be 0. So xc of 3, this is 1 modulo 5, obviously this is going to be 1. Xc of 4 is x of 2 modulo 5, which is going to be x of 2. So this is how you have to do it. Okay. Now, let me take another example just to make sure that uh, it is clear to you. So x of n, 1, 2, 0, 3. Okay. And then I need to compute x1 of n, x of n minus 3 modulo 4. This is values, the length is 4. So n minus 3 modulo 4. So I take the last three samples, which is, and put it at the beginning. So 203, 2031, which is going to be this. Is the same thing which I have explained. Okay, you have a knob, you take it in an anti-clockwise direction. But when you see a plus here, then you have to take the knob in a clockwise direction. That's the only difference. The index will remain the same. When you do that, then what happens here is you get 0, 0, 3, 1, 2 when you do x n plus 2 modulo 4. So in other words, what you are doing is that we move the first two samples at the end. Okay, so we move the first two samples to the end. So in x of n minus 3, we take the last three samples and put it at the beginning. X of n plus 2, we take the first two samples and put it at the end. Please try to understand the difference between the two, because this is very important. Again, you can do the mathematics to just cross check whether you got this right. So I'm not going to explain that in detail again. Okay. Now, what happens in terms of the time shifting property? So x of n is n point DFT is capital X of k. Is a so circular time shifting which property which we want to discuss about. So if I do the circular time shifting, x of n minus n naught modulo n, its n point DFT would be capital X of k, w, k, n naught, capital N. So if there is a plus here, then this becomes minus. Okay. All right. So this is very similar to the time shifting property of your discrete time Fourier transform, but there is a subtle difference. You have the modulo here, and again you have w term, which is nothing but a complex exponential term also, which is being added. Okay, so try to understand the subtle differences between the two particular aspects. Okay. All right, now let me take an example to illustrate this fact of how we can apply the time shifting property. Okay, circular time shifting property. Okay, I hope this is clear to you. So again, x of n minus n naught modulo n, n point DFT is capital X of k, w k, n naught n. So now what we are going to do here is, I'm going to give you an example. X of n is given as this. So it's an 8, the length is 8, n goes from 0 to 7. So x of n, it's 8 point DFT is capital X of k. Without using inverse discrete Fourier transform formula, determine a sequence y of n whose 8 point DFT is y of k is equal to w 3k 4 x of n. What is a point, n point here? Here the n point is 4, but here the n point is 8. Can I make this 4 as 8? Answer is yes. What you can do is y of k is equal to w3k4 x of k, which is nothing but e to the power of minus j 2 pi by 4 3k x of k. So if I multiply and divide by 2, then this becomes e to the power of minus j 2 pi by 8 6k x of k. So this is nothing but w 6k 8 x of k. Now if I take w 6k 8 x of k, So 6k. So this is nothing but x of n minus 6 modulo 8, because I need to get your y of n. So this is y of n is equal to x of n minus 6 modulo 8. So what is this? What we do? We take our last 6 samples starting from here, put it at the front, and the last 2 will be minus 4, 5, which you see it here. Okay. Again, mathematics, if you have understood this directly, you this initially you can do it this as an just to cross check whether you got the answer correctly. Later on, what you can do is that you can skip this particular aspect, because you since you have already got the answer. Okay, so again what I'm doing is n is equal to 0, x of minus 6 8, so x of 8 minus 6, which is x of 2, is 2, like that. Then if I put y of 7, y of 5, this is x of minus 1 modulo 8, this is x of 7, you pick the value of x of 7 and put it, and finally you're going to get the answer. Next one, the fourth property is a circular frequency shifting. Circular frequency shifting is uh, meaning that the frequency shifting is happening in DFT domain, meaning that x of n, its endpoint DFT is capital X of k. So you multiply by e to the power of j. So this you are multiplying the complex exponential term in time domain, which is e to the power of j 2 pi by capital N k naught n x of n. Its endpoint DFT is nothing but capital X of k minus k naught modulo n. Similarly, if you have a minus term here, this becomes plus. Now, the same thing, I can put it in terms of the W. So this term is nothing but W minus K naught N, capital N, X of N would be the same thing as this. Similarly, this term I can put as W N K naught N, X of N, N point DFT is capital X of K plus K naught N. Now, I'm going to go through some of the examples to make sure that you have understood how to apply the circular frequency shifting. Okay, all right. So just for a second, I'm going to give you this so that you can have a look at what I am talking about, just to get an idea about how the circular frequency shifting works. Okay, now I'll go through some examples here. So y of n is equal to cos of 2 pi by capital N times little n x of n. I want you to compute an 8-point discrete Fourier transform of x of n using the properties. Whenever you see a sine or a cos term, convert it into e to the power of j theta term. So cos theta, as you know, is half of e to the power of j theta plus half of e to the power of minus j theta. So y of n is nothing but half of e to the power of j 2 pi by capital N times little n x of n plus half of e to the power of minus j 2 pi by capital N times little n x of n. This is nothing but a circular frequency shifting property. Now, what is the value of k here? K is nothing but 1. What is the value of k here? K is nothing but minus 1. So this is half of capital X of k minus 1 modulo n plus half of capital X of k plus 1 modulo n. Okay. Now, this is one example. The another few examples are determine endpoint inverse discrete Fourier transform of x of k when it's delta of k. K goes from 0 to n minus 1 inclusive. So x of n is given by your regular formula. So in capital of X, you put delta of k. You know that it is defined only at k is equal to 0, because it's delta of k defined, meaning that the value is 1 at k is equal to 0. For other values of k, the value is going to be 0. So that means that, so this is summation. So this is going to be 1 over n. Now with that has a very important point. I'm going to compute the discrete Fourier transform of e to the power of j 2 pi by capital N k naught n. Now, what is your x of n here? Because if you have to apply the frequency shifting property, your x of n should be there, right? So your x of n is 1. So what is a DTFT of 1? So if you remember here, 1 over n, if I DTFT is delta of k, so if I multiply n on both the sides, then for a value of 1, the DTFT would be n times delta of k. So this is frequency shifting. So this becomes n times delta of k minus k naught n. Okay. Similarly, DFT of x2 of n is sine of 2 pi k naught n times capital N. That I need to compute. So this is nothing but 1 over 2j e to the power of j, this term, minus e to the power of minus j, the complete term. So this is again going to be n, the same logic here. So n divided by 2j, this is going to be delta of k minus k naught modulo n minus of delta of k plus k naught modulo n. Okay. Now I'm going to talk about circular time reversal. What is a circular time reversal? So let's think about time reversal. What happens to the time reversal? So whatever happens from n is equal to 0 to some positive value, it will be flipped to the negative aspect. Correct? So now in this case, it is modulo is there with respect to n. So xc of n is nothing but x of minus n modulo n. So how this is defined as n is equal to 0, x of 0 would be there. At n is equal to 0, the value would be the same. But from n is equal to 1 to n minus 1, the value will be flipped. So that is a circular time reversal. So like a regular even part and odd part, we have a circular even part, which is given by x ce of n is nothing but half x of n plus x of minus n modulo n. Circular odd part, which is x co of n, is nothing but half x of n minus of x of minus n modulo capital N. Instead of regular time reversal, you have a circular time reversal. That's why you get a circular even part, circular odd part. So x of n is given as 1, 2, 0, 3 as an example. So determine x1 of n, where x1 of n is nothing but x of minus n modulo 4. In that case, the origin value would remain the same, but these values would be flipped. So this becomes 3, 0, 2. So circular even part is nothing but the sample by sample you have to add and divide by 2. Circular odd part is you take this, subtract by this, and then divide by 2. Okay. Now, if you have a n-point DFT pair, which is x of n produces x of k, then if you do a circular time reversal, then there is a circular time reversal in the DFT coefficient as well. So in other words, x of k is 4 minus j2, 0 and j2, n is equal to 4. Find the DFT of x of n minus 2 modulo 4. This is going to be again the same value. 4 will be the name, but these will be flipped. So this is j2, 0 minus j2. Okay. The sixth property is circular convolution. Circular convolution is a very important property associated with discrete Fourier transform. Without so we talk about linear convolution. We talk about linear convolution is the one which we have discussed in signals and systems, but there is a very important concept of a circular convolution. So that means that in DFT domain we are doing a circular convolution. So in discrete time Fourier transform, the circular convolution, or rather the linear convolution of two sequences, results in multiplication of their respective DTFT coefficients. So here It's an n-point circular convolution we need to talk about, meaning that because it's with respect to n, x1 of n is n-point DFT is capital X1 of k, x2 of n it's n-point DFT is capital X2 of k. So now if I do a circular convolution, n-point circular convolution of n1 and n2, then my in n-point DFT, then in DFT domain it's a multiplication of the respective x1 of k times x2 of k. Okay, so the circular convolution is x3 of n is this n point circular convolution is given by this expression, which is nothing but summation of m goes from 0 to capital N minus 1, x1 of m, x2 of n minus m modulo n. This is very similar to our linear convolution formula, but the only differences are couple of them. This is with respect to the modulo which you need to put. Don't get confused with m as the variable. Usually we talk in linear convolution, it is k. There k goes from minus infinity to infinity. Here it goes with respect to m goes from 0 to n minus 1, and this is modulo n. Okay, the rest is the same. Okay, there are many ways of computing the circular convolution. So just to make the lecture a little uh, straightforward, you can compute the circular convolution using matrix. Well, there are many ways of computing. One is through the analytical method, another is a graphical method, the third one is the matrix method, fourth one is using discrete Fourier transform and inverse discrete Fourier transform method as well, which where we have used the linear transformation that would be required. So circle convolution using matrix. So I have been given the sequence x of n is 1, 2, 2, x2 of n is 1, 2, 3, 4. I want to compute a 4-point circular convolution. So the first thing is that this has 4, length is 4, but apparently this is 3. So you need to zero pad 1, 2, 2, and 0 you have to put. Now, so x3 of n is equal to x1 of n, 4-point circular convolution, that's the symbol, x2 of n. So since a 4-point, so x3 of 0, 1, 2, and 3. Now what you do is that fixed one of the um, sequence as a row column vector. So in this case, I'm going to take 1, 2, 2, 0. This one. This one, I need to make sure that it's a matrix of 4 cross 4. How I do it is, I take this entire value 1, 2, 3, and 4. Now, to get to the second column, I take this and put it up. So it dies down. So this is becomes 4, 1, 2, and 3. Again, I take this and put it up. So this becomes 3, 4, 1, 2. Again, I take this and put it up. So this becomes 2, 3, 4, 1. Because it's a 4-dimension, 4 point. So it's a 4 dimension, 4 cross 4 dimension. So if I take it up again, then this becomes 1, 2, 3, 4, which is the same thing. So I don't want to do that. So it's a 4 by 4 cross 4 matrix. And then you simplify it. Finally, you are going to get the answer as a circular convolution like this. Okay. All right. Let me stop at this point. There are some other properties are also there, which we'll discuss in the next video class. Okay. All right. I thank you very much for listening. I hope it was useful.